In this video, we're going to be talking about organizing numerical or quantitative data. All right, now that Chief-Aru has the ice cream squared away, she wants to figure out how much of their favorite soda, Orange Crush, she wants to buy. So again, she asks her friends how much soda they like and writes down the data. This type of data is quantitative data, right? It's going to be a number. And since Chief-Aru is Australian, she's going to measure it in milliliters of soda, the metric unit. All right, so here is our raw data. All right, if you look through, we have from 120 milliliters up to 1800 milliliters. All right, and again, this is just a big pile of numbers, so we need to organize it, right? So, no, the minimum was 120, the maximum was 180, and we want to break it up into classes that we can count, get a frequency and a relative frequency in each class. We want to do this by not taking each one of the numbers separately, but by binning them into classes. The first thing we need to do is decide what our class limits and class width are. So this numerical classes, let's start at 100. Let's make the class width 100 units. So the bottom of the next class is going to be 200, then 300, then 400, 500, 600, etc. Right? And this will keep going. Right? We need to have these classes go up so that we capture all of our data. So our lower class limit is going to be 100 in this class, 200 in this class, 300 in this class, etc. The upper class limit, we want to not have any overlap. We don't want it to go from 100 to 200. We want it to go from 100 to, say, 199. This means that there's a separation between the upper class limit in this class and the lower class limit in the next one. So this is going to go from 200 to 299, 300 to 399, 400 to 499, etc. And we need to make sure that we have enough classes to cover all the data. Our lowest was 120, our highest was 180. Let's take a look at what that table is going to look like. Okay, well here it is. As we see, there's a lot of classes. It's actually too big to fit on this slide. And if we look at the data, all of these are going to be empty. Right? There is no data to put in those classes. So let's be a little intelligent with our table. Let's just chop these out and make sure to put some kind of indication that we're just skipping a whole bunch of empty classes. Let's take a look at that on the next slide. So here's what I've done. I've put in this separation bar to tell me that I really have these empty classes that I'm not going to bother spending the paper to write down. So now what I want you to do is I want you to go back to look at our data set, find our frequency, which is our count again, and then calculate relative frequency. You can either do it as a percent or a proportion. Press pause and give that a try. So here's what I came up with. There was one data point in the 1800 to 1899 class that was our 1800. Our largest class remaining was the 300 to 399 milliliters. That was a third of the data, 33.3%. And again, because of rounding, I don't add up to the total 100, I add up to the 99.9%. That's good enough for the rounding that we have done. Now the next thing we want to do is we want to look at the graph of this data. And it's a particular kind of graph called a histogram. A histogram is related to a bar chart. On the x-axis, we're going to have our number values, right? In this case, it's going to be our milliliters of soda, 100, 200, 300, etc. The bottom of each of the classes, the lower class limits. The height of each bar is going to be either the frequency or the relative frequency. So the height of the bar is going to represent how much data we have in each class. And despite the fact that this class, say the 100 class, only goes up to 199, we draw that bar all the way up to 200 because a data point that's in this class could be anywhere in here. If it is 200, it's in the next class. So we only want gaps in the histogram if there's a 0 in that data, right? If there are no elements in that class. So the histogram that I've created from our table that we just did will look as follows. So here is our histogram. The 100 to 199, 200 to 299, 300 to 399, 400 to 499, right? It tells me where the 500 is. 599, 600 to 699, 700 to 799, and then we have this big gap, right? And then we have our last data point way out here at 1800. Okay. Now, we're going to talk in class about the basic shapes of distributions, but anything that is going to have a single data point way out here with a large gap, this is going to be called an outlier. There are technical ways of calculating whether or not a data point is an outlier, and we'll talk about those a little bit later in the semester. But for our intents and purposes, all of our data is down here. We have a gap that's really, really wide, and this is either someone that has a real soda addiction or they were going to type 180 and they got an extra 0 in there. So let's say that we calculated that it was a real outlier and we could ignore it. So this is our histogram that has been just pared down to the data points between 100 and 800. This is a pretty nice symmetric data. There's definitely one largest peak. The largest peak is going to be our mode. There's a secondary peak, but it's not really outstanding, so I wouldn't call this a bimodal, right? There's really only the one. Now, the bars here look pretty wide, so what we can do is we can actually cut down our data. Instead of being 100 points wide for our classes, we can cut it down to 50 points wide. I certainly encourage you to pause the video and try to do that, so their classes would be 100 to 149, 150 to 199, etc., and do the counts. The histogram for such a data set, for such a chopping up of the data, will be on the next slide. If our class width is 50, we see that the graph looks a little different, right? We now have an internal gap here. We now have a pretty decent gap in here that we didn't see when we had a class width of 100. So having smaller class widths allow us to see different features of the data that we didn't get, right? The class width of 100 kind of smeared it all out. Now, whether or not this graph looks better than the graph for the class width of 100, well, a lot of that's up to personal preference. There's a lot more bars here. There's a little more jaggediness to it. So maybe the 100 width data was sufficient, and this is just getting a little messy. But what you'll see as we go through examples in the class is that choosing different class widths makes the data look different in the distributions. And we have to make choices about whether to make our data widths narrower or wider. And a lot of it comes down to personal preference. So, I'll see you in class.